Welcome! In this session, we'll tackle an exciting problem: find a peak element 2. This problem challenges us to identify a peak element in a 2D matrix, and we'll explore different approaches to solve it. Let's dive in and break it down together. In this problem, you're given a two-dimensional integer array, also called a matrix, which we'll refer to as mat. Each entry in the matrix, represented by mat I, j, corresponds to the value at row I in column j. Your task is to find a peak element in this matrix. A peak element is defined as an element that is strictly greater than all of its adjacent elements. These adjacent elements can include the one directly above, below, to the left, or to the right of the current position, provided they exist. If a neighboring element doesn't exist, the condition simply doesn't apply to that side. The output should be the position, R, C, whereas the row index in C is the column index of any valid peak element. Importantly, it's guaranteed that at least one peak element exists in the matrix, so you don't have to handle cases where no peak is present. Finally, the input mat is a two-dimensional array with dimensions m by n, where m is the number of rows and n is the number of columns. The output for this problem is a list, R, C, which represents the row and column indices of any peak element in the matrix. To better understand this, let's consider the first example. Here, the input matrix is a simple 2 by 2 grid, 1, 4, 3, 2. In this case, the output is 0, 1, indicating that the element at row 0 in column 1 is a peak. This is because the value at that position, 4, is strictly greater than its adjacent values, 1 to its left and 2 below it. To elaborate on the first example, the element 4 at position 0, 1 is greater than both its left neighbor, which is 1, and its bottom neighbor, which is 2. Since 4 satisfies the peak condition, 0, 1 is a valid output. Remember that other valid outputs could exist if there are multiple peaks in the matrix, but 0, 1 is sufficient to solve the problem. Now, let's look at another example to deepen our understanding. For the matrix 10, 20, 15, 21, 30, 14, 7, 16, 32, the output is 1, 1. This indicates that the element at row 1, column 1, which is 30, is a peak. In the second example, the element 30 at position 1, 1 qualifies as a peak because it is strictly greater than all its neighbors. Specifically, 30 is greater than 20 above it, 16 below it, 21 to its left, and 14 to its right. This makes 1, 1 a valid peak position. Again, it's important to note that the matrix could have other peaks, but the problem allows us to return any one of them as long as it meets the definition. Now, consider the third example, which uses the matrix 10, 8, 10, 7, 9, 11, 6, 5, 4. In the third example, the output is 0, 2, which means the element at row 0, column 2, is a peak. Here, the value 10 at position 0, 2 is greater than both its left neighbor, which is 8, and its bottom neighbor, which is 11. While 0, 2 is a valid peak, it's worth noting that other positions, such as 1, 2, could also qualify as peaks. This flexibility is allowed because the problem guarantees the existence of at least one peak, and our task is simply to find any one of them. Let's now discuss some additional constraints and edge cases. First, if the matrix consists of only a single row or a single column, the peak is simply the maximum element in that row or column, as there are no other neighbors to compare against. For example, in the matrix 1, 2, 3, the peak is the maximum value, which is 3, located at position 0, 2. Second, the problem guarantees that all elements are not equal, so there will always be at least one strictly greater neighbor to form a valid peak. Finally, if there are multiple peaks in the matrix, the solution can return any one of them as long as it satisfies the peak definition. This flexibility simplifies the implementation while still adhering to the problem constraints. To begin solving the problem, the most intuitive approach is the brute force method. Here, we iterate through each cell in the 2D matrix and check if it satisfies the peak condition. For a cell to be considered a peak, its value must be greater than all its adjacent neighbors, whether up, down, left, or right, provided those neighbors exist. The process involves going row by row, column by column, and comparing the value of the current cell to its neighbors. If the condition is met, we return that cell as the peak. While this approach is simple and straightforward, its efficiency is a major drawback. The time complexity is O, m*n, where m and n represent the number of rows and columns, respectively, because we check every cell individually. The space complexity is O(1), as no additional memory is used. However, this method is not practical for large matrices since it does not take advantage of the structure of the matrix to optimize the search, leading to inefficiencies when the input size grows. To address the inefficiencies of the brute force approach, we can improve the search by applying binary search on the rows of the matrix. This method significantly reduces the number of cells we need to examine. The idea is to focus on the middle row, find the maximum element in that row, and check whether it satisfies the peak condition. If the maximum element is not a peak, we move in the direction of a larger neighbor, as a peak is guaranteed to exist in that direction due to the properties of the matrix. The steps are as follows. First, perform a binary search on the rows to identify the middle row. Then, within that row, find the column index of the maximum element. Next, compare this maximum with its vertical neighbors in the rows above and below, if they exist. If the maximum is a peak, we return it. Otherwise, we narrow our search to the half of the matrix that contains a larger neighbor. The time complexity here is O, m*log n, and the space complexity remains O(1). While this approach improves efficiency compared to brute force, it still focuses on one dimension at a time and does not fully utilize the 2D structure of the matrix. To further optimize, we can extend this idea to a two-dimensional binary search. To achieve an even more efficient solution, we apply binary search directly on the columns, which allows us to take advantage of the 2D structure of the matrix. In this approach, we perform binary search on columns rather than rows. For the middle column, we identify the row index of the maximum element and then check if this element satisfies the peak condition. Specifically, we compare the maximum element in the column with its horizontal neighbors in the left and right columns, if they exist. If this element is a peak, we return it, otherwise, we narrow the search space to the half of the matrix that contains a larger neighbor. This process is repeated until a peak is found. The time complexity of this method is O log m*n, which is more efficient than row-based binary search for certain matrix dimensions, and the space complexity remains O(1). This column-oriented binary search is fully optimized for a 2D matrix because it eliminates unnecessary rows and columns at each step, significantly reducing the search space. While it is slightly more complex to implement compared to row-based binary search, the efficiency gains make it a better choice for larger matrices. After considering the different approaches, we have chosen the column-based binary search as the strategy to solve this problem. This method is the most efficient because it narrows down the search space in both dimensions, leveraging the structure of the matrix to achieve optimal performance. By focusing on the maximum element in the middle column and iteratively reducing the search space based on the direction of larger neighbors, we ensure logarithmic complexity in one dimension while maintaining correctness. The trade-offs among the approaches are clear. The brute force method is computationally expensive and impractical for large matrices. Row-based binary search improves efficiency but still falls short of fully optimizing the 2D search space. In contrast, column-based binary search strikes the right balance between efficiency and correctness, making it the ideal choice. This strategy minimizes the search space while guaranteeing that a peak element will be found, which is why it stands out as the best solution for this problem. To solve the problem of finding a peak element in a 2D matrix, we start with the brute force approach. A peak element is defined as one that is greater than or equal to its adjacent neighbors up, down, left, and right. For boundary elements, we only consider their existing neighbors. The brute force algorithm begins by validating the input to ensure the matrix is not empty. After that, we determine the dimensions of the matrix, denoted as m for the number of rows and n for the number of columns. Next, we iterate through every cell in the matrix using nested loops. The outer loop handles the rows, while the inner loop processes the columns. For each cell, we will check if it meets the peak condition by comparing its value to its neighbors. If the cell satisfies the condition, we record its position and stop the search immediately. Now, during the neighbor comparisons, it's crucial to avoid accessing out-of-bounds indices. For the upper neighbor, we ensure the row index is greater than 0 before checking the value above. Similarly, for the lower neighbor, we verify that the row index is less than m1. The left neighbor is checked only if the column index is greater than 0, while the right neighbor is valid if the column index is less than n1. If the current cell's value is greater than or equal to all its valid neighbors, it qualifies as a peak, and we record its position. If no peak is found after traversing the entire matrix, we return a null value or an appropriate message. Additionally, special attention is given to boundary handling, as edge and corner cells have fewer neighbors, requiring specific checks to avoid errors. For example, the top left corner has only 2 neighbors, so we need to ensure those are considered properly. It's also worth noting that in any valid 2D matrix, at least one peak is guaranteed because every element has a finite number of comparisons. The brute force approach has a time complexity of O(m*n), since every cell in the matrix is checked once. Although this is straightforward, it becomes inefficient for large matrices. Still, it's a valuable starting point for understanding the problem. In terms of data structures, the matrix is stored as a 2D list where accessing any element takes constant time. Additionally, when we find a peak, its position is stored as a tuple of row and column indices. The algorithm performs at most 4 comparisons per cell, and fewer for boundary cells, ensuring that the peak condition is systematically verified. A key optimization in this approach is early termination. As soon as a peak is identified, the algorithm stops, potentially saving computation time in certain scenarios. Let's look at an example to understand the brute force approach. Consider the matrix 10, 20, 15, 21, 30, 14, 7, 16, 32. Starting at the top left corner, the value at 0, 0 is 10, and its neighbors are 20 and 21. Since 10 is less than 20, it's not a peak. Moving to 0, 1, the value is 20, and its neighbors are 10, 15, and 30. Again, 20 is less than 30, so it's not a peak. Next, we examine the cell at 1, 1, which has a value of 30. Its neighbors are 21, 14, 16, and 20. Since 30 is greater than all of these, it satisfies the peak condition. Therefore, we conclude that 1, 1 is a peak, and the algorithm returns this position immediately. Analyzing the brute force approach, the time complexity is O(m*n) due to the nested loops traversing the matrix, while the space complexity is O(1) since no additional data structures are used. However, this approach is not optimal for large matrices. To improve efficiency, we can use a divide and conquer strategy. This method reduces the search space by focusing on rows or columns with potential peaks, eliminating half of the remaining possibilities in each step. With this optimization, the time complexity improves significantly to O(m*log n, or even O(log(m*n), depending on the implementation. This makes the algorithm much more suitable for larger datasets while still guaranteeing the discovery of a peak element. This implementation solves LeetCode problem 1901 Find a peak element 2 using a binary search approach for efficient computation. A peak element in a 2D matrix is an element that is greater than or equal to its neighbors, up, down, left, right. #### code breakdown. 1. Variable initialization ***. The rows in calls variables store the dimensions of the input matrix mat. The binary search is applied column-wise, with left and right defining the current search boundaries. 2. Binary search loop ***. While left is less than or equal to right, calculate the middle column index min_call. Find the row max_row with the maximum value in the min_call. This ensures we focus on the most promising peak candidate in the current column. 3. Neighbor comparisons ***. Compare the value at max_row, min_call, with its left and right neighbors, if they exist. If this value is greater than both neighbors, it is a peak, and the function returns its position. If the right neighbor is larger, move the search to the right half by setting left equals min_call plus 1. Otherwise, move to the left half by setting right equals min_call 1. 4. Efficiency ***. This algorithm efficiently narrows down the search space in O(log) calls *rows time, using binary search on the columns and linear search on the rows. This approach ensures that the algorithm avoids brute force and scales well for larger matrices. It systematically reduces the problem size while ensuring correctness by leveraging the peak property of the elements. Here, we begin with the Java implementation of the solution. First, we define the main method, findPeakGrid, which takes a 2D matrix, mat, as input. We start by determining the number of rows and columns in the matrix using mat.length and mat0.length. Next, we initialize 2 pointers, left and right, which represent the range of columns we will search through. The binary search loop runs while left is less than or equal to right. Within the loop, we calculate the middle column, mid-col, as the average of left and right. We also initialize maxRow to 0, which will help us find the row in the middle column that contains the maximum value. To do this, we iterate through every row in the middle column, comparing values. If we find a value greater than the current maximum, we update maxRow to this new row index. After identifying the row with the maximum value in the middle column, we compare this value to its neighbors, specifically the values in the left and right columns, if they exist. The left neighbor is checked using midcol 1, and the right neighbor is checked with midcol plus 1. If the current value is greater than both neighbors, it means we have found a peak, and we return its coordinates as an array containing maxRow and midcol. However, if the value in the right neighbor is greater, it indicates the peak might lie further to the right, so we move our left pointer to midcol plus 1. On the other hand, if the value in the left neighbor is greater, we shift our search to the left by moving the right pointer to midcol 1. This binary search process ensures that we narrow down the potential columns efficiently, focusing only on the relevant portion of the matrix. Once the loop ends, the function will have returned the coordinates of a peak element. The final return statement, which provides -1, -1, is technically unreachable because the problem guarantees that a peak element always exists. This ensures the implementation aligns with the problem's constraints and avoids unnecessary edge cases. With this approach, we achieve an efficient solution with a time complexity of O, rows *log, calls, by leveraging binary search on the columns while iterating through the rows of the matrix. Here, we start with a simple 3x3 matrix and perform a step-by-step execution of our binary search approach. First, we initialize the dimensions of the matrix, so we have rows equals 3 and cols equals 3. This means we'll perform binary search on the columns, starting with left equals 0 and right equals 2. In the first iteration, we calculate the middle column using the formula, left plus right, //2, which gives us min_col equals 1. Now, we find the maximum element in column 1 by comparing each row in this column. Looking at the values, mat0, 1 equals 4, mat1, 1 equals 7, and mat2, 1 equals 2, we see that the maximum is mat1, 1 equals 7, located at max_row equals 1. Next, we compare this value with its neighbors in the same row. On the left, we have left_neighbor equals mat1, 0 equals 6. On the right, we have right_neighbor equals mat1, 2 equals 5. Since 7 is greater than both its left neighbor, 6, and its right neighbor, 5, we can conclude that 7 is a peak. The peak is located at position 1, 1, which we return as the output. This demonstrates how the binary search algorithm efficiently finds a peak in the matrix. Now, we move on to a larger 4x4 matrix. Again, we begin by initializing the dimensions, so rows equals 4 and cols equals 4. We perform binary search on the columns, starting with left equals 0 and right equals 3. In the first iteration, we calculate the middle column as min_col equals 0 plus 3, //2 equals 1. Next, we find the maximum element in column 1 by comparing all the rows in this column. The values are mat0, 1 equals 20, mat1, 1 equals 30, mat2, 1 equals 16, and mat3, 1 equals 12. The maximum value is mat1, 1 equals 30, which is located at max_row equals 1. Now, we compare this value with its neighbors. The left neighbor is left_neighbor equals mat1, 0 equals 21, and the right neighbor is right_neighbor equals mat1, 2 equals 14. Since 30 is greater than both 21 and 14, we determine that it is a peak. The peak is at position 1, 1, which we return as the output. This shows the algorithm's consistency, even with larger matrices. Next, we examine an edge case with a small 2x2 matrix. For this 2x2 matrix, we start by initializing rows equals 2 and cols equals 2. Since we're performing binary search on the columns, left equals 0 and right equals 1. In the first iteration, we calculate the middle column as min_col equals 0 plus 1, // 2 equals 0. Then, we find the maximum element in column 0 by comparing the rows. Here, mat 0, 0 equals 1 and mat 1, 0 equals 3. The maximum value is mat 1, 0 equals 3, located at max_row equals 1. Next, we compare this value with its neighbors. The left neighbor does not exist, so we treat it as negative infinity, left_neighbor equals float, inf. The right neighbor is right_neighbor equals mat 1, 1 equals 4. Since 3 is less than 4, we adjust our binary search to move right by setting left equals min_col plus 1 equals 1. In the second iteration, we calculate min_col equals 1 plus 1, // 2 equals 1. Now, we find the maximum element in column 1. Comparing the rows, mat 0, 1 equals 2 and mat 1, 1 equals 4, the maximum is mat 1, 1 equals 4, located at max_row equals 1. Finally, we compare the value 4 with its neighbors. The left neighbor is left_neighbor equals mat 1, 0 equals 3, and there is no right neighbor, so we treat it as negative infinity, right_neighbor equals float, inf. Since 4 is greater than 3 and there is no larger neighbor to the right, 4 is determined to be a peak. The peak is located at position 1, 1, and we return this as the output. This example demonstrates how the algorithm handles edge cases effectively, ensuring that it always finds a peak regardless of the matrix size or shape. In this algorithm, we use a modified binary search approach to efficiently locate a peak element in a 2D grid. The grid has dimensions n rows by m columns, and the key steps involve reducing the search space systematically. First, binary search is applied to the columns, which allows us to have the number of columns we need to consider after each iteration. This process alone takes log em iterations because the search space diminishes exponentially. For each column under consideration, we then scan all n rows to identify the row containing the maximum value in that column. This step involves n comparisons per iteration. When we combine these two processes, the overall time complexity becomes n for finding the maximum in a column, repeated log em times for the binary search. This results in a total time complexity of n*log m, which is much more efficient than a naive approach that looks at every element in the grid individually. The space complexity of this algorithm is very straightforward and efficient. It uses constant extra space, as we only maintain a small number of variables throughout the process. Specifically, variables like left, right, and min_col are used to manage the binary search, while max_row helps track the index of the maximum value in the column currently being examined. Additionally, left_neighbor and right_neighbor are used for comparisons to determine if the current element is a peak. Importantly, no additional data structures are allocated, and the input grid itself is accessed directly without any modification. This means the space complexity is 1. Now, if we compare this to a brute force approach, the naive method would involve scanning every single element in the grid, resulting in a time complexity of n*m. However, the space complexity remains 1, since no extra data structures are used in either approach. The efficiency of the current solution lies in its ability to drastically reduce the time complexity by narrowing down the search space to just log m columns while still finding the maximum value in n time for each column. When we analyze the algorithm further, we can consider the best, average, and worst-case scenarios. In the best case, the peak element is located in the very first column examined during the binary search process. While the algorithm is designed for n*log em time complexity, fewer iterations might occur in practice for this scenario due to an early termination. For the average and worst cases, the algorithm proceeds through the full binary search process, which involves log m iterations. In each of these iterations, we still scan all rows in the current column, which means the time complexity remains n*log m. The justification for this complexity lies in how binary search systematically halves the columns to consider, leading to log m iterations overall. Within each of these iterations, scanning n rows in the column takes n time, combining to n*log m as the final complexity. Additionally, since the algorithm only uses a fixed set of variables and no extra data structures, the space complexity consistently remains 1, regardless of the input size. One of the most common mistakes when solving the 2D peak finding problem is neglecting to handle edge cases, such as the boundaries of the matrix. Edge and corner cells have fewer neighbors, and failing to account for this can result in incorrect logic and missed peaks. Another pitfall is relying on brute force solutions, which involve iterating through every cell in the matrix and checking for peaks. While this approach works, it leads to an n² time complexity, which is highly inefficient for larger matrices. Instead, you should aim to optimize your solution, for example, by using divide and conquer techniques. Equally important is paying attention to the problem constraints. Certain variations might indicate that rows or columns are sorted, or they may guarantee the existence of exactly one peak. These hints are critical for developing an efficient solution. Lastly, it's important to distinguish between local and global peaks. This problem only requires finding a local peak, but some people mistakenly attempt to find the global maximum, which adds unnecessary complexity to their solution. Now, let's address another common issue: how to handle duplicates or flat regions within the matrix. When two or more adjacent cells have the same value, some solutions either skip valid peaks or enter infinite loops due to improper handling of these scenarios. To avoid this, ensure your code can correctly identify peaks in such regions. From an interview perspective, peak-related problems are designed to test your ability to optimize naive approaches and apply advanced techniques like divide and conquer. Always pay close attention to optimization hints provided in the problem, such as sorted rows or columns, as these can guide you toward better solutions like binary search. It's also crucial to clarify assumptions early in the interview. Ask questions about whether multiple peaks are allowed, if ties are considered valid peaks, and whether there are constraints on the matrix dimensions. Balancing trade-offs is another key skill. While brute force is often simpler to implement, optimized methods like binary search or divide and conquer can drastically reduce time complexity, making them more suitable for larger inputs. This problem is part of a broader category of peak finding problems, and understanding related problems can help you identify patterns and techniques. For instance, LeetCode 852, peak index in a mountain array, is a simpler one-dimensional version of the problem. Similarly, LeetCode 162, find peak element, also focuses on 1D arrays but emphasizes binary search optimization. Of course, LeetCode 1901, the problem we're discussing, is the 2D variation that builds on these concepts with additional complexity, such as handling multiple dimensions. Another related problem to consider is LeetCode 74, search a 2D matrix. While this isn't a peak finding problem, it involves applying binary search in 2 dimensions, which parallels the efficiency mindset required for solving 2D peak problems. Exploring these related problems will deepen your understanding of the techniques and strategies needed for efficient solutions. Finally, let's compare some alternative approaches to solving this problem. The brute force method, which checks every cell in the matrix to determine if it's a peak, is the simplest approach but comes with an n² time complexity, making it impractical for larger matrices. A more efficient method is binary search on rows or columns, which reduces the complexity to n*log m by focusing on one dimension at a time. Divide and conquer is another powerful approach with a time complexity of n plus m. This method involves breaking the matrix into smaller submatrices, identifying a potential peak, and recursively narrowing the search space. While efficient, it requires careful attention to boundary conditions. Another intuitive but less robust option is greedy hill climbing, where you start at a random cell and move to a neighbor with a higher value. Although this can work well in some scenarios, it may fail for matrices with specific constraints or grid layouts. Each approach has its strengths and trade-offs, so it's important to choose the one that best fits the problem's constraints and requirements. Great job! We've wrapped up the problem, find a peak element 2, and reviewed our solutions and key insights. Remember, practice is essential to mastering these concepts. Thanks for tuning in, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!